For the next few minutes, I'll be talking with you about the use of a delayed sweep time-based generator in digital applications. Most of us use a delayed sweep generator to locate and expand specific portions of a main sweep display. But once you've obtained that display, how often have you been troubled by certain display instabilities, such as jitter? How many of us use some of the additional controls of the delayed sweep, such as the ability to re-trigger the sweep after the delay interval to eliminate this jitter? Or what about multiple triggering? How often have you been frustrated by being unable to stabilize a delayed sweep display, no matter how much you adjust the trigger controls? We'll talk about a technique that will allow us to stabilize the delayed sweep display, even of the most complex waveforms, while still retaining the calibrated capability of the delayed sweep, even on time bases with a fixed trigger hold-off period. Or what about time interval measurements? Are you ever required to measure the time interval with an accuracy better than the typical 3% of the oscilloscope? We'll go through a technique that will allow us to make time interval measurements using the delayed sweep with an accuracy that approaches 1%. Well, these are exactly the applications and techniques we're going to discuss. Now, to get the most from this tape, you should have viewed the videotapes on oscilloscope basics and 180 operation. These tapes are available through the HP sales office near your area. You should have also read the operating and service manual for your particular delayed sweep generator. It should be noted at this point that although the Model 1821A delayed time-based generator will be used during most of the presentation, the features which will be exemplified are in general applicable to most delayed time-based generators. You will recall from the 180 operation tape that a delayed time-based generator requires two linear sweeps. The first is called the main sweep. And in delayed sweep applications, the main sweep is used to precisely set the delay interval. The second sweep is called the delayed sweep. And this sweep is actually used to drive the horizontal deflection system, providing the calibrated time base of the CRT display. It is important to remember that the delayed sweep is the dependent sweep. That is, it's dependent on the main sweep because it is armed by main sweep only after an adjustable delay period. Now, before we go into the uses of the delayed time-based generator in our digital applications, let's briefly review the operation of a delayed time-based sweep. And to do this, we'll use a second oscilloscope to monitor the waveforms inside the 1821A. On the monitor oscilloscope, the output of the sweep generator is being displayed. This is a linear ramp and causes the beam to move from the left to the right of the 180 CRT at a calibrated rate. To gain an adjustable delay period, we compare the main sweep to a variable DC level. The amplitude of this level is adjusted by the delay control on the front panel of the time base. At the point of coincidence, where the main sweep just equals the DC level, the delayed sweep is armed. The period of time between the beginning of the main sweep, which we can call T0, and the point of intersection, which we can call T1, is commonly known as the delay interval. Now, once the delayed sweep is armed, if the operator has selected an auto mode of delayed sweep operation, the delayed sweep will begin immediately. And notice that you have continuous control over the delay interval when you are in the auto mode. In addition to the auto mode, the operator may select a triggerable mode of operation. And in that mode, after the delayed sweep is armed, it will not begin until it receives trigger information from either an internal or an external source. And to view the difference between the triggerable modes and the auto mode, let's add another waveform to our monitor display. This waveform represents the information going to our delayed trigger generator. Notice now, by selecting an internal trigger delay situation, that as the DC level is varied, the delayed sweep jumps. The reason that it moves in this fashion is that although the delayed sweep is armed at the point of coincidence between the main sweep and the DC level, the delayed sweep is not beginning until it receives trigger information. Returning to the display on our 180, a main sweep display has been selected. And you will remember from the 180 operation tape that by turning the time per division control for the delayed sweep out of its off position, we obtain an intensified portion of our main sweep display. This intensified area represents the time window of the delayed sweep. The beginning of the time window is set by the delay control on the front panel. The width of the window is controlled by the time per division setting on the delayed sweep. This time window will be expanded to the full 10 divisions of the CRT when the operator selects delayed sweep. Most Hewlett-Packard oscilloscopes have a third mode of sweep display called mixed. In this mode, portions of the waveform are shown at both sweep settings. The early part of the waveform is shown at the slower or main sweep time-based setting, while the latter portion of the waveform is shown at the faster or delayed time-based setting. The point of crossover is again adjusted by the delay knob on the front panel. Now that we've reviewed the operation of the delayed time-based generator, let's look in detail at three of its most usable applications. If we were to look at the output of a pulse generator, for example, where each pulse is identically reproduced, one after another, we would probably find little use for a delayed time-based generator, because we can gain sufficient expansion of the waveform to capture one of the pulses and make the parameter measurements we desire. However, in digital applications, particularly with digital words, we find that the pulses are not reproduced identically. And this is particularly true in referencing to their location in time. And for those applications when we require to locate and expand a very small portion of the main sweep display, a delayed time-based generator must be used. Typical applications, because of the lack of trigger signals available, generally require us to view a main sweep that may contain 10 or 100 or 1,000 words. But our measurement requirement asks us to locate and measure only one or a portion of one of those words. By using the delayed time-based generator in conjunction with the delay control, we can do just that. The 180 has been adjusted to display 10 words on the face of the CRT. This represents one word per division. By selecting a delayed sweep time interval, the intensified area can be adjusted such that its location falls over a particular word of which you have interest. Let's say the third word in the data train. Then by selecting delayed sweep, you can magnify that word to a degree sufficient to make your measurements. So the first application of a delayed time-based generator is to locate and expand specific and small portions of the main sweep display. Now, in some cases, you may find it more convenient or find more confidence in knowing the location at which your expansion begins by using the unique mixed sweep mode. Since in this mode we view the first portion of the waveform at the main time-based setting, we always know our location when we start to expand. By adjusting the delay control, simply move that portion of the waveform you wish to view at greater resolution into the expanded area of the display and make your measurement. Other features of a delayed time-based generator allow us to obtain more stably triggered displays. There are two major sources of display instability in delayed sweep applications. The first is commonly known as jitter, which is a horizontal time shift or displacement in the waveform. Jitter is caused by the fact that the timing source or clock for our pulses is not operating at a constant frequency. It has some slight variation. And it also stands to reason that the further we delay from the beginning of our main sweep trigger point, the greater this jitter or time displacement becomes. And in some applications, particularly on magnetic tapes, the jitter becomes so great that we can no longer view or make measurements on our pulses. To overcome or eliminate jitter, the triggerable feature of the delayed time-based generator is quite helpful, because by selecting a triggerable mode, and in this example internal triggering is being used, the delayed sweep will begin only if it receives trigger information after the delay interval has occurred. So by re-triggering delayed sweep after the adjustable delay period, the effect of jitter is eliminated on your display. The second major source of unstable displays is somewhat more complex. It results from a phenomenon known as multiple triggering. Let's first take an example where multiple triggering causes an unstable display, and then look in detail at its cause. For a stable display to occur on the CRT, the operation of the oscilloscope, that is, the period between one sweep and the next, must identically match the period of the repeatable portion of the waveform we're viewing. Let's take, for example, a single word length. If we were viewing this word, and we obtained one sweep per word, we obtain a stable display. Returning to our monitor oscilloscope, let's look at the input waveform. It's a rather simple 16-bit word with 4 of the bits as true. And we find that when we view the main sweep out of the 1821A, instead of having 4 sweeps during a period of 4 words, we actually have 8. Those additional sweeps are causing the instability. Expanding our monitor display, we can more easily see why the instability exists. Because during the first sweep, for example, we view that portion of the word containing 3 of the 4 true bits. But the second sweep views the remaining portion of the word with only 1 of the true bits seen. So on alternate sweeps, we are viewing different portions of the same word, and therefore see an instability on the 180 CRT. So to overcome the instability, remember the criterion for a stable display to occur. That is, somehow the period from one sweep to the next must match the repeatable portion of the repeatable period of the incoming waveform. Some time-based generators, for example the 1822A, have a control on the front panel known as variable trigger hold-off. This control allows the operator to adjust the time between the end of one sweep and the beginning of the next, and therefore controls the operation or period of operation of the oscilloscope. Adjusting the control varies the period of time that trigger information is held off from the delayed sweep circuits after the occurrence of the last sweep. If the hold-off period is increased long enough, in our example here, the trigger from the 4th true bit is held off, eliminating the additional sweep, causing the instability of the display. And now we're only viewing those sweeps that look at that portion of the incoming word where 3 of the bits are true. However, most delayed time-based generators in use today don't have this variable hold-off control. The trigger hold-off period is fixed and is internally set within the instrument. For those instruments, such as the 1821A, we must find another technique to overcome multiple triggering. Again, to adjust the period of operation of the scope, we could leave the trigger hold-off period fixed, but this time vary the length of time of each sweep. This would effectively result in the same change of period. To do this on an oscilloscope with a time-based unit that does not have a variable hold-off control, simply take the main time-based vernier out of its calibrated position and rotate it until the display becomes stable. What has occurred is that by adjusting the main sweep vernier control, the length of the sweep increased, moving the fixed hold-off period out to coincide with the occurrence of the 4th true bit. The trigger information resulting from that bit is therefore rejected, and the additional sweeps causing the instability no longer occur. Now let me go over that again. For time-based generators that do not have a variable hold-off control, simply take the main time-based vernier out of its calibrated position and rotate it until the display becomes stable. Now we have a stable display, but we are only viewing a portion of the word. So you can rotate the control a little further and view the entire word, or rotate it still further and possibly obtain multiple words on the same display. But it's obvious that we can no longer make calibrated time measurements on the main sweep display, since the vernier control is out of its calibrated position. And this is where the advantage of a delayed time-based generator comes into effect. Because in a delayed generator, we have a second sweep, a delayed sweep, which remains in calibration. So once the operator has stabilized his display by using the main vernier control, he simply selects a delayed sweep display, positions the waveform where he wants it, and expands it to the desired resolution to make his measurements, this time with a calibrated 3% time base. Now let's focus our attention on the third major capability of a delayed time-based generator. Since the conception of an oscilloscope, it's been used to make time measurements as well as amplitude measurements. And with a single time-based generator, the oscilloscope was used to make time measurements by simply comparing the waveform to the graticule on the CRT. For those time measurements, since the sweep was calibrated, the operator could obtain a measurement of time comparing the waveform to the graticule. And in present-day oscilloscopes, the accuracy of that measurement is typically plus or minus 3%. Well, a little earlier I alluded to the fact that with the delayed time-based generator we can make time interval measurements whose accuracy approaches 1%. Let's take a look at how we can do this. Let's take an example that requires us to measure the time between the beginning of one pulse and the beginning of the next. If we were going to make this measurement using a single time-based generator only, we would adjust the horizontal and vertical controls to gain the maximum visual resolution possible, and then position the beginning of the first pulse to a convenient graticule line, and simply count or measure the divisions to the beginning of the second pulse. In our example here, it's 7.2 divisions. Now to compute the time measurement, why, of course, we take the number of divisions times the main time-based setting, which in this case is 10 microseconds, and we add or subtract plus or minus 3% for our accuracy. So that for time interval measurements using a single time base only is now 72 microseconds plus or minus 3%. This 3% represents 2.2 microseconds, so our total answer is 72 plus or minus 2.2 microseconds. To understand how we could use a delayed time-based generator to gain greater accuracy, we must first understand what causes this 3% accuracy error when using a single time base. And it turns out the error comes from two sources. First, the error or inaccuracy in the sweep waveform itself internal to the time base. This has to do with errors in its slope due to the timing components, and also nonlinearity errors. For typical oscilloscopes today, this error, that is of the sweep waveform itself, is typically in the area of 1%. The additional 2% inaccuracy comes from the horizontal amplifier and the nonlinearity of the CRT. So to use a delayed time base to gain greater accuracy, we will have to develop or come up with a technique that will allow us to eliminate the inaccuracy caused by the horizontal amplifier and the CRT. And it would probably be a little more meaningful if we would first go through the technique and then come back and determine why this occurs. First, obtain a display of the time interval. In our case, this is the time between the beginning of the two pulses on the main sweep display. Now select a delayed sweep display and position the beginning of the first pulse using the delay control to a convenient location on the graticule. Let's say center screen. Now, note the reading on the delay control, 0.45. Now, using the delay control, position the beginning of the second pulse to the same point on the face of the CRT as we positioned the beginning of the first. And again, note the reading on the delay control. now 7.67. The difference of the two readings, in this case 7.22 divisions, represents the divisions of the delay on the main sweep. To convert this to time, we must multiply this number times the main time-based setting, not the delayed, but the main time-based setting. And this gives us 72.2 microseconds. Now, what we have really done to eliminate the inaccuracy of the CRT and the horizontal amplifier is simply to use the CRT as a nulling device. Remember, each time we took our measurements, that is, we measured the beginning and we measured the end of the delay interval, we referenced the waveform to the same location on the CRT. This tends to nullify the effect of the nonlinearity of the CRT and the horizontal amplifier. And so our accuracy now is simply the accuracy with which we can set the delay interval. That accuracy of the delay interval has two components. First of all, the accuracy of the sweep internal to the time base. And second of all, the accuracy of the delay control. That is, the ability or accuracy with which we can set the DC level. For our time base, the sweep accuracy is typically plus or minus 1% of the reading. So in our case, this would be 1% of 7.22 divisions we measured on the waveform. The delay control accuracy, however, is specified as a percent of the maximum delay period. The maximum delay period is simply the total delay that we can obtain on our display. Or more simply, the total delay that we could obtain is the length, the total length of the main sweep display. If we are setting, as we are in this example, with a main sweep display of 10 microseconds per division, our maximum delay is 10 divisions. So our maximum delay period is now 10 divisions times 10 microseconds, or 100 microseconds long. The percentage of inaccuracy for the delay control itself is specified as plus or minus 0.2% of the maximum delay period. So now to compute our reading and its accuracy, we take the plus or minus 1% of our reading, which was 72.2 microseconds, plus or minus 0.2% of the maximum delay period, which in this case is 100 microseconds. And this converts to an error of plus or minus 0.72 microseconds. This is the error due to the sweep. Plus or minus an additional 0.2 microseconds due to the delay control, or a total inaccuracy of plus or minus 0.92 microseconds. This is approximately 2.5 times better than the accuracy we had using a single time base and measuring the time interval with the graticule on the CRT. Now notice that in computing the delay accuracy, we would approach, but never quite equal, 1% measurements. This is because of the inaccuracy of the delay control. But notice that if we can reduce the maximum delay period, we could reduce or eventually approach the 1% accuracy of the sweep. And how do we do this? Well, simply by using the fastest possible main sweep display we can. This reduces the total or maximum delay period. The limitation here is that the time interval, that is both the beginning and the end of the time interval, must be displayed on the main sweep display on the CRT. Otherwise, you could never locate either one or the other of the points of the time interval you are measuring using the delayed sweep generator. In the last few minutes, you have seen that although we all use a delayed time-based generator as a magnifier, it has some additional powerful tools which will help you in your measurement applications. Specifically, it has the capability of allowing you to stably trigger a display even of the most complex waveform information. And it also allows you to make very accurate time interval measurements, the accuracy of which will approach 1%. Should you have any specialized applications which the information of this videotape hasn't covered, please don't hesitate to contact your HP field engineer and ask for his assistance.